Hi, computer science students. Hope all is well. Hope everybody is doing good. I miss seeing you guys as always. And normally this would be a big celebration because this is going to be the last day of notes. I know we've got a few more pages left, but I think we're pretty good after this. So, happy last day of notes. Here we are on block 7. Okay, so in RFC, the request for comments protocols for the internet, 3271, the internet is for everyone. Vint Cerf, the father of the internet, wrote, "Let us dedicate ourselves to the proposition that cryptographic technology sufficient to protect privacy from unauthorized disclosure should be freely available, applicable, and exportable." Okay, so what does this mean? Well, this means that the internet is for everyone, but it won't be if users cannot protect their privacy and the confidentiality of transactions conducted on the network. So we need to be aware of whether our data is being encrypted, so be educated consumers of technology, but we don't have to be able to create our own cryptographic methods and tools. The tools exist and are freely and publicly available. Okay? So why might it be a good thing that encryption algorithms are freely shared so that anybody who wishes can try to crack them? Okay, so again, going back to our example from last time, you know how to work a lock and key. So if you looked at my keychain, I only have 4 or 5 keys on there, and it would be easy for you to figure out which one of those opens my classroom or my house or my car, right? But if you think of like a custodian's key ring that has lots and lots of keys, you know how it works, but it would take a really long time, okay? So it's a good thing. So even though everybody knows what's going on with the encryption method, the lock and key, it's still going to take a while for you to crack this. So if the security of an encryption technique relies solely on the method remaining it a secret, it might not actually be all that secure. Ideally, a method will be so secure that even if you know the technique that it was used, it is computationally hard to crack the message. Would a heuristic be useful in decryption? So remember, heuristic means approximate solution. And the answer is no, not usually. Usually we need to know an exact number. Okay? If you're trying to get into my bank account, you probably want the exact number. Having an approximate is not super helpful. So by making encryption techniques public, we want them to open up to being tested by anyone who wishes to ensure that there are no clever ways of cracking the encryption. So what we're focusing on for the rest of the day today is computationally hard problems. These are problems that force a computer to run through many possibilities to find the right answer. In cryptography, our desire to have an encryption function that is easy to compute if you have the key, but really hard if you don't. Today we're going to look at one of the most famous problems that is thought to be computationally hard. We'll see if we can find an algorithm to solve it, and along the way we'll get a better sense of what computationally hard means. So this is called the traveling salesperson problem. So let me give you a little bit of background first. The traveling salesperson problem imagines that a salesperson starting at his home or office needs to visit a number of customers at different locations. The goal is for the salesperson to visit each location exactly once and end up back where he started as efficiently as possible without retracing any part of the route. The problem, given a graph of nodes and edges where the weights of the edges represent some cost, that is distance or time or money, find the set of edges that make the lowest cost tour of all nodes. A tour is a route that visits each node exactly once and returns to the start. Think about somebody who's delivering something, right? In the age right now of Grubhub. So what makes the most sense? Do you go to the restaurant and then where do you go next? The farthest away, the closest? There must be one route that saves you the least amount of time, right? And also uses the least amount of gas. So this problem was first formulated in 1930 and is one of the most intensively studied problems in optimization because it has many applications in the real world. Almost any business that involves transportation of any kind is concerned with this problem, and there are direct costs in time, money, and resources into taking inefficient paths to visit all the nodes. Okay, for example, flipping the page here. A mail carrier delivering mail must go to each house exactly once and needs to end up at the starting location and wants to minimize the length of the route. So for example, this graph shows the direct route between stores and the distance from each route. You can assume that any node is your home or the starting point. So here are some possible routes that visit every node exactly once and return to where you started. So let's go ahead and do some math here. So the first one, it says we're going to start at B. Then we go to A, which is 2. And from A, we go to D, which is 12. And from D, we go to E, which is 10. And E, we go to C, which is 3. And from C, we go back to B, which is 4. Okay, so what is 2 plus 12 plus 10 plus 3 plus 4? For those of you who are not good with the mental math, 31 is the correct answer. Okay, so that would be how long it would take to go. So we went from B to A to D to E. So that doesn't seem, crazy. So let's go ahead and look at another route. So this one starts at A. So it goes from A to E to D to C. Okay, so A to E is 5. E to D is 10. D to C is 3. C to B is 4. And B to A is 2. So what is 5 plus 10 plus 3 plus 4 plus 2? Well, FYI, this gives you 24. So the shortest route that visits every node once and returns to where you started is that second one, our AECB, DBA. Okay, so again, this is a different one. That's why it didn't make sense. Okay, so this one is A, E, C, B, D, A. So A, E, C, B, D, and A. Okay, so this particular distance is 21. Okay, so there's definitely sort of like a right way to do this. You know what I mean? There's one that is definitely better. Let's look at another one here. So try to find the shortest path for this graph. As you work, think about your own process. Could you write a strategy as an algorithm? Okay, so I want you to go ahead and pause the video, and I want you to figure out what you've got, and we'll talk in just a second. Okay, so what did you look at? Let's say, for example, you did like all the way around, right? So let's say you did A, E, D, C, B, A. So that's all around the edges. This gives you 13, okay? That is definitely not the best though. There are two paths that I found that give you better results. I had A, B, E, D, C, A, B, E, D, C, A, okay? I found that gave you 9, and also D, C, A, B, E, D, D, C, A, B, E, D, okay? Also gave you 9, okay? How would you go ahead and describe your thinking? Did you maybe try to stay on shorter paths? Did you try all the possibilities, changing one path at a time? Okay, it's really hard to write an algorithm in terms of the way you think, right? So many people for years have tried to design an algorithm that works in all cases to find the exact optimum route for the traveling salesperson problem with no success. So currently there is no algorithm to find the exact answer besides brute force, meaning trying all the possibilities. Since we have to calculate the distance for all tours anyways, we might as well count how many tours there are in the first place, just so we know how many calculations we have to perform. So for this demonstration, let's also consider a version of this problem faced by, say, an airline. So for an airline, there are cities all over the world, and you can fly from any one directly to another. So for an airline, there is a possible path that connects every possible node. Okay, so we would say that the graph is fully connected. Let's see how the problem goes quickly by constructing all the possible tours for larger and larger numbers of nodes. Okay, so let's start with just 3 nodes here. When we only have 3 nodes, or 3 cities if we're thinking of this as an airplane, there is only one possibility. Easy. But with 4 nodes, now there are 3 possibilities. You could go this way, or this way, or this way. Okay, so that's still not bad. Now here's where it starts to get crazy. With 5 nodes, there are 12 possible tours. How can you figure this out? Well, the way shown below has to reason that the 5th node could be added between each pair of nodes for every possible 4th tour. So here the actual distance don't matter because we're just trying to count the number of possibilities. So below is another view of the same thing. In this version, we just took each 4-node tour and broke one of the edges, connecting it to a new 5th node. Just a different way to think about it. So for 6 nodes, we could repeat the process again. Add a node to every possible edge of the 12 solutions for the 5 nodes. Since each of the 12 solutions has 5 edges, it means we have 12 times 5, or 60 tours. Notice how fast this grows. Between a graph with 3 nodes and a graph of 6 nodes, our total number of tours grew from 1 to 60. So the problem grows very quickly, which means with just 10 nodes, or 10 cities you're trying to go to, or 10 mailboxes you're trying to go to, this grows to about 181,440 possible tours. Or with just 26 nodes, this grows to a 25-digit number. I'm not even going to attempt to say this, but look at how crazy this is. By comparison, the width of the entire observable universe in miles is roughly a 25-digit number. With up to 100 nodes or 100 mailboxes, or think about a UPS deliverer right now, they probably are delivering to 100 houses, you're up to roughly a 155-digit number. Phew! Computers work fast, but they have limits. In computer science, we have actual mathematical, a hard line between reasonable and unreasonable run times. Reasonable means that the number of things the computer has to do is proportional to the size of the input problem. Unreasonable means that the number of things the computer has to do grows as an exponent of the size of the input. In real life, unreasonable problems would take a modern computer trillions and trillions of years to churn through all the possibilities. So brute force solution to the traveling salesperson problem is unreasonable, at least as far as we know. And in fact, it's an open question of how to solve this problem efficiently. If anyone finds a solution that runs in a reasonable time, a lot of security and encryption algorithms are in trouble, because many are based in the fact that this and related problems are unreasonable to solve. again, so think about it. Let's say, for example, I put $1 million in a bank vault and I tell you that I have the key. It's on this key ring. This key ring has this number of keys. All you need to do is to find the correct key and the money is yours. Well, think about how long you would have to do, how many keys you'd have to go through in order to find the right one. You might get lucky, but probably not. Okay, that's why things are secure, because even though you know how to solve the problem, it just takes you a really, really long time to do so. Okay, so that's how, even though people know how everything is encrypted, they just still can't hack through it because it takes way too long. All right, happy last day of notes in computer science. Bye, friends.